Okay, so today we're going to kick off our next unit, which will be taking a little bit more in-depth look at some of the aspects of trigonometry we've been discussing lately. And one of the first things we're going to talk about is the ways angles can be measured. We're pretty familiar with some ways, but we'll be looking at another technique that we will use a lot in this unit. First off, we want to talk about exactly what an angle is and maybe a concept of something that we haven't really thought of it in a way. An angle is formed by two rays that share a common endpoint known as the vertex, and I'm sure we're all familiar with that definition. But what we're going to be thinking about here in this unit, we'll be thinking in particular that one of the rays is fixed, meaning it's not moving, and we'll call that the initial side of the angle. And then we have another ray that is being rotated around the vertex, and we'll think of that as the terminal side of the angle. You can kind of think of this as a door swinging open, or even if you wanted to kind of think about the hands on a clock, one of the hands staying still, and we'd call that the fixed side, and then the other hand rotating around. That would be the terminal side, the terminal meaning where it ends. The measure of an angle is the amount of rotation that is required to move from the initial side to the terminal side. So we can kind of think of an angle as being an initial side. Again, that say both of them started in the same location, and the other one, the terminal side, rotated over a certain number of degrees or a certain distance, and that distance of rotation would be the measurement of the angle. So you can kind of think of it as being on a hinge and rotating around that hinge. Now, we like to talk about angles being in standard position. And standard position is what we call the position where we say the initial side of the angle is located on the x-axis, and the vertex of the angle would be at the origin. And we could kind of produce a coordinate grid or a coordinate plane to fit on any angle in that manner. If we rotate the terminal side counterclockwise, meaning rotating to the left, that would give us a positive angle measure. And we'll look at some examples here in a minute. If we rotate it to the clockwise direction, meaning to the right, that would give us a negative angle measure. So we have positive angles and we have negative angles. And really, the only difference between the two is the direction that the angle is moving. The degree is the most common unit of angle measurement. However, we're going to look at some other ones here in a minute, or another one, not other ones, just one more. But we typically, in common speak, we usually use the degree as the unit of angle measurement. However, there's another one that we'll be using here that applies to certain situations that we'll be doing a lot. But before we get into that, we're going to discuss something we call coterminal angles. Now, terminal again is the side that the angle opens up to. When an angle is in standard position and it makes a full rotation, that would be a 360 degree angle, meaning it goes all the way around. A measure that is greater than 360 degrees represents more than one rotation. So we can actually have more than 360 degrees. Say we had 720 degrees. That would be two full rotations around. So it's not hard to draw a 720 degree angle, but we could have that. We could have a 540 degree angle, which would be one full rotation and another half of a rotation. Angles that have the same standard position would be called coterminal angles. So 360 degrees and 720 degrees, since they end up in the same place, they're what we call coterminal angles. So coterminal angles may be in the same location but have different measures. And they're going to always differ by a multiple of 360. Basically, we're just adding 360 on every time to get to the next coterminal angle. So this is something that a concept that some people kind of get hung up on, and it's a little confusing, but let me kind of spell this out for you a little better, and we can take a look at something here. Say we have an angle, or say we have a coordinate grid, and we're going to we're going to have an angle put on there, and we're going to have it in standard position, meaning its initial side would be here, and it's going to open up some number of degrees. Say we have a 100-degree angle. Okay, that would be about right here. And we said that was 100 degrees. So this is a rotation that moves in this direction. Now, we could have another angle going in the same direction, but it went more than one full rotation around. Say that'd be 360 degrees, and it went all the way back around here. So if it just rotated around, we would refer to this as the same angle. It would be a coterminal angle because it's ending in the same spot. But that rotation would be way more than 100 degrees. In fact, it would be 460 degrees because it went around to the same location. Likewise, we could also go around in the opposite direction. And if I went, say, around here, back that way, that would start at 0 and rotate around this way. And that would be negative 260 degrees. Because it's negative because it went in the clockwise direction. And it would be 260 degrees. So negative 260, 100, and 460 are all what we would call coterminal angles. And my handwriting there is pretty rough, but that's coterminal, meaning they're all the same. They all have the same end point. So when we're looking at what we call coterminal angles, we might be looking at the same angle with a different numerical value to represent it. So let's look at an example here where we might be talking about the angle of 45 degrees. And we're asked to identify all the angles that are coterminal with that given angle. Well, we could write out an expression. Obviously, I can keep adding 360 and I can keep rotating around, and there's not going to be really a limit to the number of angles I can come up with that would be coterminal with it. But we would write an expression here to basically say 45 plus 360 times k, and k would be the number of rotations we were going to go around before we hit our next one. So that's just an algebraic expression to represent all of the angles that would be coterminal with a 45-degree angle. Excuse me. A positive coterminal angle, we're going to come up with two actual values here, one positive, one negative. So to get a positive coterminal angle, we're basically going to just take 45 degrees and we're going to add on a full rotation, which would be 360 degrees. So that would give me 405. 360 plus, or 45 plus 360 degrees would be 405. We could also have a negative rotation, meaning going to the opposite direction. So if we started at 45 degrees and we went around in the other direction, we would basically subtract 360 from that 45, and we would get negative 315 degrees. So 45 degrees, 405 degrees, negative 315 degrees, they're all in the same location. Now we take the angle 250 degrees. And, if we wanted to write an expression to represent all coterminal angles with that, it would be 250 plus 360k. And if we wanted to find a positive coterminal angle with a 250-degree angle, that would be 250 plus 360, and that's going to be 610 degrees. If we wanted to find a negative coterminal angle, we would basically take 250 and subtract 360 from it, meaning we're just rotating around the opposite direction. So that would give me negative 110 degrees. Again, they're just coterminal angles, meaning anytime I talk about a negative 110 degree angle, it has all of the properties that a 250 degree angle would have. It would be in the same location as a 610 degree angle. It would look exactly the same. Now, let's get to the other way that we can measure angles, now that we've kind of talked a little bit about what angles are and how they work together. When we're in situations where we're really referring to distances of rotations and whatnot, we're doing applications where it would not be an appropriate measurement if we were to use degrees. So when we're dealing with distance traveled through a rotation, we would not use a degree measurement. We would use something we call radian measures. And you've probably noticed on your calculator we have the radian mode and degree mode. And up to this point, I've always told you to use the degree mode. We want to look at a way of measuring using radians, which is another mode you can use on your calculator, and we'll talk about that later on. But first off, what is a radian? A radian is based on the portion of the circumference of the circle or a circular rotation that the angle is forming on our unit circle. And a unit circle we'll talk more about in the next couple of days. A unit circle is a circle with a radius of 1. But for the most part, we don't really need to understand that at this point. We need to understand that the circumference is based on a distance of 2 pi, and the amount of that angle that the amount of that circle that we're using with our angle is what makes the radian measure of that angle. So a full rotation, like I said, of a unit circle, that would be a circle with a radius of 1, would correspond to an angle with a measure of 2 pi radians. So one full rotation is 2 pi radians. Another way of thinking of that is 360 degrees is the equivalent of 2 pi radians. And the reason for that is because, excuse me, if we have a circle that has a radius of 1, and you go back and you refresh yourself on the formula for circumference, or basically which the distance around the outside of a circle, is based on the formula 2 pi r, 2 times pi times the radius, or pi times diameter. And if our radius is 1, our circumference is 2 pi. So based on that idea, that would mean 360 degrees is 2 pi, and we would simplify that down to be pi radians is the equivalent of 180 degrees. So we can always convert between degrees and radians by using this one conversion factor, that 180 degrees is equal to pi radians. So let's look at an example here where we're changing an angle that's in degree form to radian measure. So we take 330 degrees, we convert it to radian measure in terms of pi, meaning we're just going to use the pi symbol here. We would take 330 and we're going to multiply by 1, meaning we're not going to change the value, but we're going to do it in the form of our conversion factor so that our degrees will cancel. So, man, I just apologize for that G symbol there. My computer is interpreting the multiplication symbol as G for some reason right now. I need to update some things, but we're going to multiply 330 degrees times pi radians over 180 degrees. It's a fraction. Since pi and 180 degrees are the equivalent of each other, that's basically multiplying it by 1. So 330 times pi divided by 180 is what we have. Now we would just simplify this. 330 over 180 can simplify to 11 over 6. So we have 11 pi over 6 radians. So 11 pi over 6 is the equivalent of 330 degrees. And that's a measurement in radians that we'll be working with a little bit more in the future. Say we wanted to take a measurement in radians, such as 5 pi over 9, and convert it to degree measure. So we would just basically do the same thing, except we're trying to cancel out the pi, and we're going to end up with radian or degrees. So we want to put the degrees on top of the conversion factor now, so that the degrees don't cancel out, they're left behind, and the pi will cancel out with the radian measure. So we'll take this and basically flip it over so the pi's cancel out, and we'll take 180 degrees over pi radians. So I just want to emphasize the point here. If we're changing to radians, we put radians on top and degrees on the bottom because we're canceling out degrees. If we're we're converting to degrees, we put the degrees on top and we put the radians on the bottom so that they cancel out. So you basically want to cancel out your units here and leave behind the one that you're trying to get. So we multiply 5 pi times 180 degrees. We're going to divide by 9. That gives us 900 degrees. The pi's cancel out over 9, and that of course simplifies to be 100 degrees. So 5 pi over 9 would be the equivalent of 100 degrees. Now, one other application, or one of the main applications we use with radian measure, is the measurement of arc lengths. Now, an arc is just a portion of a circle, or a portion of the outside part of a circle. And if we wanted to know that distance, which would be very important, say if we were studying the rotation of something, we would want to know the arc length. The arc length is based on a measure of radians. And we basically would take that arc length, or we would get that arc length by taking the radian measure and multiplying it times the radius of the circle, or the rotation that it's taking. So we formulate that as the angle of S, which is the symbol for arc length, equals R, which is radian, or our radius, and we're going to multiply that R times theta, which is our measurement of the angle in radians. So for example, we have we want to find the length of an arc formed by a central angle of 128 degrees in a circle with a radius of 5 centimeters. So first off, we would want to take that 128 degrees and convert it to radians. So we take that, multiply it by pi over 180. So we have 128 pi over 180. That simplifies to 32 pi over 45. Then we're going to want to multiply that times 5 centimeters. And then we simplify everything, and we get that our arc length is 32 pi over 9 centimeters. Okay, so that's in simplest form, so we would just leave it as that, and that would be the length of our arc. If we wanted to get a decimal, we would basically convert, we just punch in 32 times pi and divide it by 9, and that would come out to be approximately 11.17 centimeters. So an object rotating in a circle with a radius of 5 centimeters that rotated 128 degrees would travel a distance of 11.17 centimeters. Okay, so let's take a look at some practice problems here. Just want to get a feel for working with some of these. The math is not too complicated, however, just some concepts that you kind of just need to get used to talking about. So our first practice example will be to identify all angles that are coterminal with a given angle, and then we want to find one positive and one negative angle that is coterminal with the angle 22 degrees. So we have a 22 degree angle, and we want to find all of the measurements that are the same as that, or located in the same position. So if we thought of ourselves on a coordinate grid, and we looked at a 22 degree angle, which would probably be somewhere around here, we could go 22 degrees. And another way to do that would be to rotate around here, and we would get that by adding one full rotation around. Or we could go in that from that place to here, the other direction. So one way to write the expression for all the angles would be to just say we're taking 22 and we're going to add 360 times some number of rotations, and that would give us our coterminal angles for all of them. Another way, or to just name one positive, name a positive angle, that would be taking this red path here. That would be traveling around 22 degrees and then traveling around another 360 from there. So that would be 360 plus 22, which would be 382 degrees. And if we were going along the green path, going in the opposite direction from 22 back around this way, we would take 22 and subtract 360, and 22 minus 360 is going to be negative 338 degrees. And that would basically be, the answer to that question. And it's not very complicated. You just need to kind of understand the concept. We're adding 360, we're subtracting 360, basically because we're just going one full rotation around. Okay? So let's look at the next practice problem. And, I know that if you're watching this, you can pause the video and kind of answer these before I share the answers. I'm not going to sit here and do the door of the Explorer and just stare at the screen while you're working it. So now we have a 240 degree angle, and we want to change it to radian measure in terms of pi. I forgot to put the pi symbol in there. But we have a 240 degree angle. And basically, to change that in terms of pi, we're going to take 240 degrees and we're going to multiply it times pi over 180 degrees. 240 times pi, of course, is 240 pi over 180. And we would simplify 240 pi, or 240 over 180. I believe 60 goes into both of those. So we would get our final answer as being 4 pi over 3. Over 3 radians. That would be our measurement in radian form. Okay, in our next problem, we're going to take let me see if I can get another color up here, and we'll take 570 degrees. We're going to get it in radian form. We're going to multiply by pi over 180. So we have 570 pi divided by 180. Now that's going to simplify. I believe 30 goes into both of those. And we would be simplified down to 19 pi over 6. So that would be the radian form of our angle measure. Now let's take a look at how it works when we're going the opposite way. Now remember, we said if we wanted to get to radians, we would put radians on top, meaning our pi would go on top and our degrees would go on the bottom because we were trying to cancel out degrees. So now we're doing it the other way. We want to take our degrees, or we're taking our radians, and we want to convert to degrees. So we're going to put the radians on the bottom and we'll put the degrees on the top because we're trying to get degrees. So we'll put 180 degrees on top and we'll put the pi on the bottom. So what happens is we have 3 times 180 is 540 pi over 2 pi. Now you'll see when you look at this, pi's are going to cancel out, and we can simplify down. 540 over 2 would simplify to be 270 degrees. And you'll notice the degree symbol was on top here. So that basically got us to where we are, 270 degrees as being our measurement, 3 pi over 2. Now, here's another one that people tend to look at and get a little confused because they look at this and they say, well, that's not in radian measure, it's negative 1.75. It can be a decimal. Radian measure typically would be a decimal if we took the pi and multiplied it in using the keys on our calculator, usually. So I'm still going to convert the same way. I'm going to take 180 degrees because I'm trying to get degrees. I put it on top. And I'm trying to cancel out radians, so I put pi radians on the bottom. So we multiply negative 1.75 times 180, and that becomes negative 315 over pi. And then basically we would just simplify that by dividing by pi. And I would actually recommend that you use the pi key on your calculator. And what you do when you get that, it's going to come out to be about negative 100.3 degrees. And remember, we can get negative degrees. That just basically means we're rotating clockwise instead of counterclockwise, meaning we're rotating to the right instead of the left. All right, in our last practice problem here, we're going to find the length of an arc that is intercepted by a central angle of 5 pi over 6. So let's say we got a circle here. I'm going to try and draw one out. And if we're going to have a circle there, and we have a center, let's say I'm going to try and eyeball it. Say it's right there. And our standard position comes out from here and goes to 5 pi over 6, which is going to be about there. Just to give you a concept in degrees, 5 pi over 6 is 150 degrees. But that's where our distance would be. So this, let's say this is 5 pi over 6, and let's say I can write that a little bit better than I just did. So let's try that again. Oh man. Okay, so I just experienced a little glitch there. Sorry about that. So we're back on, and you can see I typed in instead of dealing with the last dealing with the pen. 5 pi over 6 is our angle measurement, and it's going basically, it's rotating around this way. And what we want to know is the arc length, which is going to be the distance that we are traveling along this path if we're rotating around a circle that is 15 inches in radius. So this would be our arc length. You know, we're going to get that by working our formula that S is equal to R theta. And in this case, R is 15 and theta is 5 pi over 6. So we take 15 times 5 pi over 6, and of course that's going to be 75 pi over 6. And you're going to basically punch that in to a calculator, and you're going to get that this length is about 39.3, I'm getting 39.27 inches. That would be the length of that arc. In other words, if I traveled from this point, point A, to point B, going around the outside of this circle, I would be traveling that distance. So that's one use of radian measure, and there are a few others that will apply in class, but you're going to see this one probably in your upcoming assignments, probably more than anything else right now. So make sure you're aware of arc length. All right, that's our lesson for today. Please feel free to ask questions in class, and we'll talk more about this, and we'll discuss it then. Have a great day.